The really important thing here is that policy iteration does not get stuck in the local optimum. That is to say, if there's any way to improve, it will actually improve. It won't get stuck before. So the important step in the proof for that is actually back one slide when we talked about value non-deprovement, or what I called value improvement. So I went back a slide so we can look at this together. So so this is the claim that I'm making, Charles, that if it's the case that pi 1 is optimal, then the greedy policy pi 2 with respect to the fixed point of the pi 1 is going to be the same. We're actually going to be stuck at the fixed point, because that's the whole thing about being a fixed point. But if it's not, then there has to be at least one state someplace where this value non-deprovement is actually value improvement, like strict value improvement for some state like that. Boom.
I see. So what's really going on here is we should be more precise maybe about what value improvement really means, or what value non-deprovement means.
Okay.
We're talking about it, every time we talk about it in terms of one value function better than another. And so it's easy to think of it that way. But if that were the case, then I could have sort of cycles, right? Where, I have two states where I keep on each iteration swapping back and forth which one is better than the other. And you'd still have domination in both cases, right? Does that make sense, what I just said?
Wait, no, because domination is point-wise, it's state-wise.
Yes, it is state-wise, but imagine I had two states, let's call them S1 and S2. And let's say for one particular value function, if I were going to compare, let's say Q1 and Q2, or V1 and V2, it's going to compare V1 and V2. It turns out that in S1, V1 is greater than it is in V2. So just make up some numbers, right? And in the other case, they're the same.
The same.
Yeah.
Okay.
Then I could apply an operator to both of them. It would also be the case. So here V1 dominates V2, right?
Right.
So here's another set of numbers I could write down where V1 still dominates V2.
Okay.
So rewrite the S1 and S2 again underneath.
All right. So V1 still dominates V2.
Right. So V1 still dominates V2 if I just swap the two rows around. And so if you weren't thinking carefully about what value improvement or value non-deprovement meant, you would think that you could just go back and forth between these two different values where 10.6 and 3.3, those rows sort of swap, because in both cases, you're still getting V1 dominating V2. But it's actually the case that the way this value improvement works is that it's true not just for the overall value functions, it's true at every state.
Oh, I see. Yes, that it can't be the case that we go from V1 have S1 being 10 to V1 S1 being 3, because it's actually non-deproving.
Right.
In other words, we can't go down. We can stay the same, but we can't go down.
Right. So the statement has to be the case for all the states as well as the overall set of states. So once V1 is better than V2 in some state, it basically has to stay that way.
Got it.
So this keeps us from cycling back and forth, and this is what keeps us from getting in a kind of get sort of locally stuck. That's my claim.
Okay. All right. So local stuckness doesn't happen.
Mm-hmm.
And in particular, we get strict value improvement in at least one state if we haven't actually reached the fixed point yet. And therefore, each time we go through policy iteration, it's actually getting better until it can't get better anymore. So one other interesting thing to point out is that the number of policies, each time that we go through an iteration of policy iteration, we have a new deterministic policy. There's just a finite number of them. Therefore, at some point, we exhaust the set of possible improvements that we can make, and we have to have found the optimal policy.
You know what that reminds me of?
EM.
Oh, close though.
Okay.
Reminds me of the proof we had for why K-means had to converge.
Oh, yes. It's exactly the same argument. Yeah. When we talked about K-means in the other class, we talked about how there's a finite set of assignments that can be made, and each time you do an iteration of K-means, we get either the same assignment or one that has a better score, and therefore we're going to find the one with the best score.
Well, we're going to find a one that doesn't change anymore. But the difference between Kmeans proof and this is that you could get stuck in a local optimum.
In K-means.
K-means, but here you can. And I think the big difference is that you basically, its statement of value non-deprovement is at every single point, every single state in this case. Whereas with K-means, that wasn't necessarily the case.
Okay, super. So do you feel like you have you're grokking policy iteration now?
Yeah, in particular, I'm grokking that it actually kind of has to work. That's sort of cool.
Cool. I think we can sum up then.
Let's sum up. I like summing up.